Welcome! Today, we're unlocking an entirely invisible world that literally surrounds us all the time. We're talking about the fascinating, hidden language of chemical changes. Every single day, right in front of our eyes, microscopic atoms are breaking bonds, making brand new ones, and fundamentally altering the universe around us. It's happening right now. So we're going to decode exactly how that works. Here is our roadmap for today. First up, we'll look at spotting reactions in the wild. Then, we'll figure out how to balance equations. Third, we're looking at the 5 core types of reactions. And finally, we'll wrap up with how everyday chemistry directly impacts your daily life. Okay, let's dive into this. Part 1, spotting chemical reactions, or finding clues of the invisible. How do we actually act as detectives to know a chemical reaction is taking place? Well, think about this for a second. What do a piece of rusting iron, a batch of fermenting grapes, and the food currently digesting in your stomach all have in common? In every single one of these scenarios, the nature and identity of the initial substance completely changes. It's not just a physical shift, like an ice cube melting into water. The actual chemical identity is transformed into something entirely new. To spot these hidden transformations, we rely on 4 primary sensory clues. A reaction might cause a sudden change in state or a really dramatic shift in color. We might see the evolution of a gas, like bubbling, or feel a noticeable change in temperature. For instance, if you burn a magnesium ribbon, you don't just get a new white powder at the end, you get a dazzling, brilliant white flame. Or if you heat ferrous sulfate crystals, you can physically smell the characteristic sharp odor of burning sulfur as gases are released. These are the visceral, real-world signs of invisible bonds breaking apart. Moving right along to part 2, balancing chemical equations. This is essentially the grammar of chemistry. To communicate these chemical changes accurately, we need mathematical grammar. And the absolute golden rule of this grammar is the law of conservation of mass. It states that mass can neither be created nor destroyed in a chemical reaction. Think of it like a ledger in accounting. The exact number of atoms you start with before a reaction must perfectly equal what remains after. You can't just lose an atom of iron into the void or, magically summon oxygen out of thin air. Now, if we tally up the atoms for a reaction between iron and water, we run into a really interesting puzzle. On the starting side, the reactants, we have exactly 1 iron atom. But on the resulting side, the products, we suddenly have 3. And the oxygen? It unexpectedly jumps from 1 to 4. This is what we call an unbalanced skeletal equation. It totally violates our golden rule because the mass is just not the same on both sides. So how do we solve this puzzle? We use what's called the hit and trial method. First, you conceptually draw boxes around each formula to remind yourself to never change the formulas themselves, meaning you absolutely cannot change H2O into H2O4 just to make the math work. Second, you start balancing with a compound that has the maximum number of atoms. Then you methodically balance the remaining elements one by one, adding whole number coefficients in front of those boxes. And finally, you do a strict audit, double-checking the correctness of all the atoms on both sides. Let's see how this builds into our final result. By adding a 3 in front of the iron and a 4 in front of both the water and the hydrogen gas, both sides now perfectly match. We've also added state symbols, S for solid, G for gas. Notice that water here has a G next to it? That adds a crucial piece of real-world context, telling us that the water is actually being used in the form of steam. All right, section 3, the 5 types of reactions. Think of these as chemistry's core plot lines. Almost every chemical reaction falls into one of 5 main genres. Let's look at the first 2, which are essentially opposites. In combination reactions, 2 or more reactants combine to build a single new product. It's just like mashing 2 pieces of clay together. Conversely, decomposition reactions involve a single reactant breaking down into simpler products. Think of it like taking apart a giant Lego tower. So one builds up and the other breaks apart. Another super important way to categorize reactions is by how they handle energy. Exothermic reactions release heat, literally making the mixture warm to the touch. Endothermic reactions are the exact opposite. They absorb energy, whether that's heat, light, or electricity, to force the reaction to even happen. And here's a crazy fact for you. Human respiration is an exothermic reaction. When your cells break down glucose to keep you alive, that very process releases the energy you need to survive. Moving to our third type, we have displacement reactions. This is basically the chemistry equivalent of someone stealing your seat. It happens when a more reactive element aggressively displaces or kicks out a less reactive element from its compound. If you drop a shiny iron nail into a bright blue copper sulfate solution, over time, that nail turns brownish, and that vivid blue color slowly fades away. And the equation for this brilliantly illustrates exactly what's happening in that test tube. The iron is more reactive than the copper, so the iron steps right in, pushes the copper completely out of the way, and binds with the sulfate itself. The poor copper is left all alone as a solid brown deposit. So the key takeaway there is that in a single displacement, one element swaps in, but in a double displacement reaction, two compounds essentially trade dance partners. There is a mutual exchange of ions between the reactants. A classic hallmark of this is when you mix two perfectly clear liquid solutions, like sodium sulfate and barium chloride, and suddenly, boom, a white, insoluble powder instantly appears out of nowhere. We call that solid a precipitate. Finally, our fifth type is the oxidation reduction, or redox reaction. This is all about the flow of oxygen or hydrogen. Simply put, if a substance gains oxygen, it is oxidized. If it loses oxygen, it's reduced. In this scenario with copper oxide and hydrogen, the copper oxide loses its oxygen to become plain copper, so it is reduced. Simultaneously, the hydrogen gas gains that very same oxygen to become water, so it is oxidized. They always happen together as a pair. Let's wrap things up with Section 4, Everyday Chemistry. This is the everyday reality. We've spent a lot of time looking at microscopic letters and numbers. Let's zoom back out to see how these exact reactions impact us on a daily basis. First up is corrosion. When a metal is attacked by moisture, acids, or oxygen in the air, it begins to corrode. The most famous example is, of course, the reddish-brown rusting of iron, but copper getting a green coating or your silver jewelry turning black, that's corrosion too. This insidious process causes enormous financial and structural damage to car bodies, bridges, and ships every single year. But oxidation doesn't just attack metal, it actually attacks your food. Have you ever opened an old bag of nuts or used some old cooking oil and noticed a harsh, stale, almost paint-like smell? That is rancidity. It occurs when fats and oils are oxidized over time. The chemical structure of the fat actually breaks down, completely ruining the smell and the taste. To fight this, food producers have to use chemistry to their advantage. Here's a fantastic cocktail party fact for you. Have you ever wondered why potato chip bags are so puffy? Manufacturers deliberately flush those bags with nitrogen gas. By removing the oxygen and replacing it with unreactive nitrogen, they literally stop the oxidation reaction in its tracks, preventing the chips from going rancid before you even open them. And that brings us full circle. Chemistry isn't just some textbook subject. It is the active, dynamic operating system of the physical world. From the rust weakening a steel bridge, to the nitrogen protecting your snacks, to the exothermic energy keeping your very cells alive. So I'll leave you with this. Look around the room you're in right now. What invisible chemical reaction is quietly transforming the world around you at this very second?